In this video, we're going to talk about division of power series. In the last one, we saw how we could use a basic elementary school, high school algebra um, algorithm for multiplying uh, numbers, polynomials, power series to help us multiply power series. We could use a similar long division algorithm to help us divide polynomials and divide power series. So let's do a power series for tangent of x, a Maclaurin series. We're going to do it by realizing that tangent of x is sine of x divided by cosine x, and we're going to take the series for sine of x given here and divide it by the series for cosine x. Now remember, sine x, here it is in summation form, cosine x, here it is in summation form, but sine x is just x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the seventh, and so forth. It's an alternating series with only odd power terms. Similarly, cosine is only even power terms, and it's an alternating series, the even power, and then we have 1 over that even power factorial for the coefficient, plus or minus. Okay, so dividing those out, we can just use our basic long division algorithm. So this written out is x minus 1/6 x cubed plus 1 over 120 x to the fifth minus 1 over 5040 x to the seventh plus other terms. For sine x, that's the numerator or the dividend, and the denominator or divisor is 1 minus 1/2 x squared plus 1 over 24 x to the fourth minus 1 over 720 x to the sixth plus more terms. And we just divide this out with our basic division algorithm, just like we did in elementary school. X divided by 1 is x, x times 1 is x, x times negative 1/2 x squared is negative 1/2 x cubed, x times 1/24 x to the fourth is 1/24 x to the fifth, x times negative 1 over 720 x to the sixth is negative 1 over 720 x to the seventh. Now we need to subtract. This cancels out. Negative 1/6 plus 1/2 is negative 1/6 plus 3/6, which is 2/6. So that's 2/3 x to the third. 1 over 120 minus 1 over 24 is 1 over 120 minus 5 over 120, which is negative 4 over 120, which reduces to negative 1 over 30. And then we can do this, negative 1 over 5040 minus plus 1 over 720. We get a common denominator of 5040 and work that out. I'm going to just verify these things that I have here using a calculator. Of course, you could do these by hand, but we have a negative 1 over 5040 minus, and then a fraction, I'm sorry, it is actually plus 1 over 720 because we're subtracting, right? So the signs have to change on the bottom one. So change that to plus, and that is, it didn't like that. Let's go back and figure out what happened here. Oh. Okay. And that's 1 over 840. All right, now we divide the next one out. 1/3 x cubed divided by 1 is 1/3 x cubed. Multiply there, we get 1/3 x cubed. 1/3, so x cubed times x to the second is x to the fifth, so it lines up there. 1/3 times negative 1/2 is negative 1/6. This becomes x to the 3 plus 4 is 7. And 1/3 times 1/24 is 1 over 72. And then some other terms. And some other terms we don't care about. Subtract, this is 0. I think I can do this one in my head. Negative 1/30 plus 1/6, this is 5/30 minus 1/30 is 4/30, which reduces to 2/15. Let me just go ahead and do this one with the calculator here. It is 1 over 840 and then minus, oops, there, minus 1 over 72. Of course, we could get a common denominator here and do this. Not terribly hard to do that, but we get negative 4 over 315 there. All right, 2/15 x to the fifth divided by 1 is 2/15 x to the fifth. Multiply here, we get 2/15 x to the fifth. We get an x to the seventh term here, which is 2/15 times a negative 1/2. The 2's cancel, you get a negative 1/15 there, and some more stuff. Subtract, we get, I'll do it over here, negative 4 over 3/15, and then plus 1/15. It's not too hard to do this by hand, but it just takes some time. 1/15, that is, right there. And that turns out to be 17 over 315 for that coefficient there. Divide that by 1, you get 17 over 315 x to the seventh, and more stuff. Okay, so we don't really worry about the and more stuff. We've got our first 1, 2, 3, 4 terms that are not 0, which actually had to take us up all the way to the 7th power because of all the missing terms. It turns out to be only odd terms here. So there's our first part, at least, of our infinite series. For tangent of x, it's x plus 1/3 x cubed plus 2/15 x to the fifth plus 17 over 135 x to the seventh. Now, we haven't really established a real good pattern for what's meant by that dot, 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 so it's kind of hard to see how this continues on. So we don't really know what the next term is going to be, or the next one, or the next one. We could have gotten more terms if we needed it by, expanding this out to keep track of what the next term is here. Okay, if we were to do this by hand and get this many terms out, we'd need to find at least the 7th degree Taylor polynomial for this. That would require us to find 7 derivatives. Here they are worked out. Starts out not too bad. The derivative tangent is 1 over cosine square, or secant square. The derivative of that is, well, written in terms of sines and cosines, it's 2 sine of x cosine cubed of x. The derivative of that is right here. The derivative of that is here. The derivative of that is big enough it won't even fit on the screen, so I had to scroll over to see the rest of it here. The derivative of that is getting seriously kind of nasty now. It's this. Here's the first part of it. Here's kind of the middle part. And here's the end of it. We're not done yet. Then we have to take the derivative of that mess, which runs across these 3 screens here. Oh, 4, 5 screens runs across. Okay, well, I think it suffices to say we really wouldn't want to be doing that by hand. And we're still not even done, right? Because then we have to evaluate all of that at x equals 0 and then divide by n factorial to get the nth coefficient, right? And so that is something we'd really, I'd rather not do that. Okay. The good news is the TI Inspire calculator actually will use Taylor's theorem and do this out directly and work it out, and it will give us a Taylor polynomial. The command is Taylor function variable, and then I think you can put in, I think right here you might be able to put in like x minus 1 or something for where it's centered. But if it's just a Maclaurin series, Maclaurin polynomial, Taylor polynomial centered at 0, we would center this at x, and then put the 7th degree here, and there it is. It works out at just what we did above. So it's much quicker with the technology. But if you had to do this by hand, you really wouldn't want to do it that way. Here's working out a couple more terms all the way up to the 11th degree polynomial to see that you only have the odd terms surviving there. And again, this was particularly nasty to do directly, but not terribly bad to do this way here with the long division. The long division is not super easy. There's some fraction arithmetic in particular that we had to keep up with here, but still not too bad to come up with this, especially not compared to this mess, right? Okay, next video we'll come back and talk about applying some of these ideas to the binomial series, which is a pretty important one.